Hello, welcome to this video on electromagnetic induction, and this is one of the most interesting I think topics of electromagnetism, definitely in within the GCSE syllabus. And so I hope within one or two videos I can give you a good sense of what's going on with induction, how to calculate what direction currents are induced in circuits, and the kinds of uses that you can put this phenomenon to. And then we'll do a few questions on this topic, so that we can also see how what kinds of things we can be asked and what kinds of answers we expect. Right. So one thing that's important to note, one thing that you should know is that for a circuit, it's important that the circuit, an electric circuit, is closed, right? So it always has to be closed all the way so that you get currents. And the only way you can really create a current is if there is an EMF. An EMF, which means an electromotive force. It's not really a force, but it's the name they gave it a long time ago and then stayed like that. But it's definitely the potential difference created which makes the electrons move around. So in other words, if you have a battery, for example, here, that can create the potential difference, then that provides the energy for the electrons to move around. If the electrons move around in this direction, sorry, I've drawn the long side on here, so that's the positive current convention in which the current would be taken to move, but the actual electrons go in the opposite direction, in that direction. I know I say that very often, but it's important to remember. Now, you can create an EMF not only by using a battery, but you can also create an electromotive force, and this I find pretty interesting. If, for example, you had a magnet like this, north pole there and a south pole here, and you have a wire going through it like that. Let me use a different color for the wires. You have a wire like that, and imagine this is closed circuit wire, right? This is closed. And here the magnetic field lines, if we drew them, they're not really there, but we draw them just to have a sense of what direction the field lines are pointing. And so imagine that that's a pretty constant uniform magnetic field. You can get an EMF created in this wire, i.e. you can get electrons going around it, and a current created by just moving this guy inside of this magnetic field. If you just move it, and what we call it, if you cut the magnetic field lines through here with the wire, then you get electrons going around. It's as if you had a battery somehow. So then you're actually doing the work of the battery yourself with your muscles by moving that wire. I find that really interesting, and that's one of the ways that the dynamo works on your bicycle. If you used to have one of those headlights that works, the harder you cycle around, the brighter they get. Then this is how they work. They have some kind of wire system like this, where you have a permanent magnet, two permanent magnets like this, or one which is curled around. You can also, this could be just one, this could be just the same magnet, right, curled around like that. And then, but this wouldn't work very well because you wouldn't be able to spin this thing as you cycle around. But ideally, it can spin through there. So then it would probably be two magnets like that. And then this would spin around and just go around and around and around. And because of the permanent magnet, and you're cutting the field lines, then you would get an EMF, and the electric charge would then move around the circuit. And then if you had a bulb here, then it would shine. Right. So this was all discovered by this guy called Faraday, who was Fleming, really. Mainly Fleming, who's really good experimental physicist, and did loads of stuff with electromagnetism. And so having introduced that, I'll be a little bit more organized in the way that I present this. And so let's get chatting a little bit more about induction. So in formal physics terms, and we all love formal physics terms, what we say is that an EMF is induced in the wire. So if the wire forms part of a complete circuit, the EMF makes a current flow. So we can say that this effect is called electromagnetic induction. So we can say that an EMF is induced in the wire when this happens. Okay, that would be if they ask you to explain what's happening here, then you could say that because a wire with a closed circuit wire is cutting magnetic field lines, then an EMF is induced in the wire. So this happens whenever a closed circuits wire is moved and cuts. Well, it doesn't have to be moved, it can happen the other way around, but the wire cuts through magnetic field lines. So in other words, if the wire was like in this direction, completely along the line of the magnetic field lines, and then we moved it around but it wasn't cutting any of the lines, then you wouldn't get any induced EMF, right? It needs to be cutting them, so cutting them in some way. It's important to know that there has to be motion, it has to be cutting them. It's got to do with the rate of cutting them. So but with how fast you're cutting the line. So if you just left it there, then there wouldn't be an EMF induced. Okay, you don't get so much of a benefit from it. You don't get a free sort of current there going by just leaving that there and letting the magnetism do the work. You've got to move with respect to the field lines, and then you can get an EMF can be induced. So I hope that makes sense. So normally these currents are quite small. You can do tricks with them, like putting many more turns of these wires and moving them very fast and stuff like that to get bigger currents. But if you just did this experiment here and this magnet wasn't so powerful, you would have a very small current. So normally you would have to attach on this circuit something called a galvanometer, which is a very sensitive device to small currents. So then you could register what direction this moves, if it swings that way or it swings that way, and that depends on the direction in which you move it and all sorts of other stuff. Okay, so I hear you asking what way can we increase to increase the EMF or the current. The EMF and the current, really one will produce the other. Then how do we do this? Well, there's several ways. One of the important ones is to move the wire faster. So move the wire faster. I hope you're taking notes of all of this, because it's very useful stuff. You need to know it for these tests. So move the wire faster is one way. The second one is to use a stronger magnet. So you can use stronger magnets. Right, either of these two will make you will produce a larger EMF. And the third one is that you can increase the length of wire in the magnetic field. So for example, here you could loop more turns of the wire. So basically you come here and you say, okay, well, I can do it only once like that, or I can continue. If I had more wire and it was longer, then here after one loop I could have another loop here like that, and then I could have a third loop, and you could have as many loops as you wanted. And the more loops you had, the more, you know what happened there. So let's do another couple of loops. Okay. Then the more loops that there would be there, then when you move this, you're cutting many more times more the field lines. There's many more field lines you're cutting in every given second as you move it around. And since the EMF depends on how fast you're cutting the field lines, that would do it. If there's 4 turns, I would do it 4 times faster, so then the EMF would be bigger, and here in the galvanometer you would register a much bigger current than, say, if you only had 1 turn. Okay, so hopefully that makes sense, and we need to write this down also in green. And so we increase the length of the wire in the magnetic field, so we can increase the length of wire in the magnetic field. The B field is the same thing as a magnetic field, really. And for example, you can loop them around several times, as we just said. Now all of these ideas are summed up really by Faraday's law of electromagnetic induction. So it was I got confused about that before. It was Faraday that was doing this really. Fleming was also very influential with his hand rules, but this was Faraday who was doing the induction stuff. So what's Faraday's law of Faraday? I don't know how you pronounce his name, but I say Faraday's law of induction. Let's see, what was that? Of electromagnetic induction really, but you can write it like that. It says the EMF induced in a conductor is proportional to what? It's proportional to the rate at which magnetic field lines are cut by the conductor. So magnetic field lines are cut by the conductor. So you can imagine this guy ages ago in his garage just with wires, and then he's got a magnet here and another magnet there, and he's got a wire, and he starts moving this wire around, and he connects a galvanometer here to see if there is any current or not, and suddenly he starts seeing that the more he moves and the stronger the magnet and the more turns, then the bigger the current. So he says, hey, this might have a use to it, and it does. It has a lot of uses, and really a lot of the ways we generate electricity have to do with this. This is a very, very important law, and I'll give you an example. If you had well, the way any generator really uses this, but if you have water, so you have a cliff, it's really important for, well, windmills and hydropower stations and anything like that. But imagine you had loads of water here and they're falling there because of gravity, and then when they get here to the bottom they hit some kind of generator like that, and this thing turns, and as it turns you get this into a large magnetic field, and as it turns you get wires placed like this, coils, cleverly, and as they turn inside of the magnetic field you allow the water to do all the work and to push these things around, and because of that huge motion you can get here on really big turning generator things. I don't know the word for them right now. Then you can get loads of EMF created, and you can produce power that way, and then you can feed that into the grid, and this is completely renewable. It's really the sun that is heating the water when it's then at the bottom and it goes back to the lake or a sea or something here. Then the sun shines on that. The sun's probably not blue, neither it is yellow, but all these photons of light come in and they shine on the water, and the water gets evaporated, and so it goes up because of the difference of density, and then it rains again when it gets to the top from the clouds, and then over and over you go again. So it's really the sun doing all of this work, and we just soak it all up and smile, get ready. So it's a very good way of doing this, but obviously it's limited to places where you get this kind of accumulation of water, and you need to do a dam, and that stops the water flowing, and there's all sorts of considerations to have with that, and we have to be a little bit careful when we mess with the ecology like that. But it's a great idea nonetheless, and that all came from good old Faraday and these ideas. So I'm running out of time, but that serves me well for waffling so much. But I will continue talking about induction in the next video, and hopefully see you there soon.